Hello and welcome to today's archive. This is about atoms and starlight. In particular, what we're going to discuss today is how we get information from very distant objects. Now, it's important to understand that in many ways, astronomy is a very difficult science in the respect that you can't perform very many experiments within the laboratory. It's certainly possible to do experiments where on a small scale, you simulate things like different gases to simulations on chemistry, nuclear reactions. But for the most part, when we're gathering our evidence, we're doing so from quite a large distance. Sometimes we're fortunate enough that the objects that we're investigating are close enough that we can send a robotic explorer there. We've been able to land on the moon and take samples from the moon, but most of our investigation of the solar system actually comes from robotic space probes. Right now there's a very sophisticated robotic space probe, a lander on Mars called Curiosity, which is taking different samples and analyzing them on board the rover. But again, the solar system is such a small part of what we investigate in astronomy that most of the objects are at such a great distance. When you consider that we are one astronomical unit from the sun, millions of miles, and when you compare that to stars, a star is light years away, and one light year is 63,000 astronomical units. You can understand that the prospect with the current technology of traveling to these locations is just impossible. So we have to get our information from a very great distance, and the only thing that can travel across space very efficiently is light. Well, there are other types of radiation that do travel great distances, but they're more difficult to handle, more difficult to detect. So really, light, or more properly, electromagnetic radiation is where we're going to get almost all our information from distant objects in the heavens. So today we're going to talk about different sources of light, mechanisms that produce this light. We'll talk about black-body radiation, or black-body spectra. This is produced by the thermal properties of matter. So they tell us a lot about the temperature of what we're looking at. We'll talk about atomic spectra. When the density of a gas is rather low, it produces either a bright line spectra or a dark line spectra, depending on its temperature and the temperature of the objects behind it. Molecular spectra, at low enough temperatures, molecules do form. They have a different spectra than individual atoms. We'll talk about spectra of minerals, and again, going back to Mars, it's very important to be able to understand what type of light minerals will absorb. And then finally, we'll talk about Doppler shift, which tells us a lot about the speed an object is traveling. So let's start with black-body spectra. The term black-body comes from the fact that objects that are completely black, and nothing is completely black out there, everything, with the exception of a black hole, either reflects a little bit of light or absorbs a little bit of, reflects a little bit of light and doesn't absorb all the light that falls on it. But a true black body, this theoretical construct, is something that would absorb all energy and re-radiate it according to its temperature. Now, for an object to emit this type of radiation, it has to be dense. All dense objects will give off some thermal energy in the form of this electromagnetic radiation. And when we say dense, anything denser than a gas of density like we might find in our own atmosphere. Again, we call it black-body radiation because dark objects tend to radiate more radiation than lighter objects, as well as the fact that dark objects absorb light more easily. The process of radiating light especially if it's visible light, is called incandescence. Again, it's another term for black body or thermal radiation. And if you've ever watched hot coals on like a barbecue, you can see the reddish-orange light that they give off. This glow is thermal radiation. Old, inefficient incandescent bulbs, the type that Thomas Edison invented or perfected, gave off, once again, this radiation, this visible light, due to its temperature. So, again, these are good everyday examples of systems that glow because they're hot. Now, if something is white hot, okay, hot enough to glow in all parts of the visible spectrum, we're talking about something that's extremely hot, probably between 6,000 and 7,000 degrees Kelvin. White hot objects are giving off a nearly equal amount of radiation in the red, in the green, and the blue part of the spectrum. So because they're white hot, because they're giving off all these colors, they appear white. White is the sum of all colors put together. The sun is a very good example of something that is nearly white hot, or gives off nearly white continuous light. And again, that's the photosphere of the sun, and that's extremely, extremely hot compared to anything we find on the Earth. One thing that we find when we look at objects and the black body radiation that they give off is that the wavelength or the frequency of light that they give off is strongly dependent on the temperature. So the coldest objects in the universe still glow. For instance, space itself glows, and this glow is left over from the actual Big Bang. And while the Big Bang was probably the hottest event that ever occurred in the universe, the entire universe was nearly equally hot at this point in time. The universe has expanded dramatically, and as a result of this expansion, it's also cooled off quite a bit. Now, radio waves are the longest wavelength. Microwaves are the second longest wavelength. So really, really cold objects, only a couple degrees Kelvin, would glow very weakly in the microwave part of the spectrum. Planets like Jupiter are still hot from their formation. Planets in general, which go around the sun, even when they're not being illuminated by the sun, generally would glow in the infrared. And again, stars are even hotter, so they would glow at the next part of the spectrum. We go from microwaves to infrared. The next part, the part that we can actually see, is visible light. Here's a chart of different black body spectra and the different temperatures of these objects and also where they glow. So let's start at about 200 degrees Kelvin. That's very, very cold. That would probably be pretty close to the coldest temperature that we'd find on the Earth. You can see here that it glows only in the infrared part of the spectrum. So if you were to visualize something that's very cold, it would give off very little black body radiation, give off very little infrared light, and this light would mainly be in part of the spectrum that we can't see. Our body temperatures at 300 degrees Kelvin, approximately 300 degrees Kelvin, are warmer. So we give off more infrared light, and therefore we glow stronger in the infrared. And if you use night vision, you can actually see, night vision uses infrared, you can actually see people, very easily because we glow much brighter than our surroundings. At 400K, it still glows almost entirely in the infrared part of the spectrum. 600K, still not hot enough to see any visible light. But at 1,000 degrees Kelvin, like the hot coals that we saw, we start seeing quite a bit of red light, quite a bit of orange, a little less yellow, and other parts of the spectrum. That's why they sort of produce this orangish red glow when they're hot. They're not as hot as the sun, so the light is very red, but they're much, much hotter than other objects. At 2,000 degrees Kelvin, this would be probably what you'd find from an incandescent filament. You can see that it still glows stronger in the red than the blue. That's why incandescent bulbs sort of have this warmer glow to them, the more reddish glow. But, certainly the blue is a little better balanced here. At 4,000 degrees Kelvin, it evens out a little better. At 6,000 degrees Kelvin, it nearly becomes white. But also notice that these hotter objects still give off quite a bit of infrared light, more than their colder components, or counterparts. When you get hot enough, they're also emitting quite a bit in the ultraviolet. So again, at 1,000 degrees Kelvin, we generally see things that are red hot, things like hot coals. And you can tell that most of the radiation that these objects give off is infrared light, because if you hold your hands up to them, you can feel the radiation. It feels hot. That infrared light is very easily absorbed by your skin, converted into heat. At 2,000 degrees Kelvin, like the incandescent bulb, again, although the light appears to be whitish to us, look at that picture of that filament. There's definitely sort of a orangish yellow, tint to it. And that is due to the curve that you see in the graph below. At 6,000 degrees Kelvin, again, similar to the sun, it peaks somewhere in the yellow. But if you really look at the sun, it's hard to see that much yellow in there. It really looks very white when we look at it. So again, looking at objects that are similar temperatures to things we find on our Earth, ourselves, the background, those things tend to glow in the infrared. When we talk about stars are incredibly hot compared to terrestrial temperatures, and therefore they'll glow at a higher frequency part of the spectrum, visible light part. So when we start getting into even shorter parts of the spectrum, let's say ultraviolet, then we're talking about even hotter objects. For instance, the corona of the sun has a very low density. So there aren't a lot of atoms there, so there's not a lot of total heat there. But the low density plasma that does make up the corona glows mainly in the ultraviolet part of the spectrum rather than the visible part of the spectrum. The surface of blue stars are much, much hotter than the surface of the sun. Although they give off a large amount of visible light, they also give off much more ultraviolet light than our own sun. Bumping up to an even higher frequency part of the spectrum. In astronomy, if we see things glowing strongly in the X-ray, and this is due to black-body radiation, then we know that these are significantly hotter than objects that we see in our own solar system, well over 1 million degrees. At that temperature, things are going to glow very strongly in the X-ray. Solar flares give off a tremendous amount of X-ray light. That's when the gas in the corona is superheated by a strong change in the magnetic field. Neutron stars, such as the one that's shown here, this is an image shown of from the Chandra X-ray telescope. The radiation from the neutron star heats up its surroundings to very high temperatures, and it glows strongly in the X-ray. And finally, one of the strongest sources of X-ray is the black hole. Now, a black hole in itself is black. It doesn't give off radiation. However, as matter falls into the black hole, a region around the black hole called an accretion disk, through friction and other processes, superheats the matter before it finally spirals into the black hole. This generates very hot jets of energy and matter, and these jets reach extremely, extremely high temperatures, again in the millions. So we know that it is at a very high temperature. And again, a big giveaway for the existence of a black hole oftentimes is the presence of very intense X-ray radiation. Now, the shortest wavelength, highest frequency part of the electromagnetic spectrum is the gamma ray part. So here we imagine that temperatures are so incredibly hot. We're probably talking about billions of degrees. Now, gamma rays are typically emitted by radioactive atomic nuclei. That isn't a temperature thing. That is completely a nuclear physics process. However, in extremely rare cataclysmic events, such as what's shown here, two neutron stars merging, you can have a tremendous release of energy. And again, temperatures involving billions or even trillions of degrees Kelvin. When this happens, we get what's called a gamma ray burst, where the material from the object is heated to such extreme temperatures that it glows in the X-ray. When the largest stars explode, they also can produce an intense burst of energy. And gamma ray bursts can also be indicative of the dying of the most massive of stars. So there you go. You look at the different parts of the spectrum, and a lot of times you can measure the temperature of an object simply looking at the temperature that it gives, the radiation that it gives off. In fact, if you want a nice application of this, look at the example of an ear thermometer. An ear thermometer looks at the infrared light that your ear canal and inner ear give off, or middle ear give off. And by measuring the frequency and the intensity of this light, it can come up with a very accurate temperature for your core temperature. Same thing in astronomy. It's almost like we stick one of these ear thermometers to the sky. When we look at the radiation coming from these denser objects, and we look at the frequencies of light, which are given off, we can come up with a very accurate temperature of whatever phenomena we're observing. So really, there's a first piece of information that we can get, a very important piece of information, because temperature is oftentimes associated with energy. We want to find out how much energy a particular event involves. Temperature tells us a lot about that event. Now let's look at atomic spectra, a little bit different. Most objects that are very dense, we're not going to get atomic spectra from. Okay, most dense objects. You know, the sun is a big ball of hot gas, but even the photosphere is much denser than what we typically see in atomic spectrum from. We do see lines in the sun spectra, but it's dominated primarily by continuous spectra from the dense photosphere. With the atomic spectra, we're looking at either a very low density gas, or we're looking at a low density plasma. Now, every atom has a specific set of electron energies. And these energies really create a fingerprint for what light can be given off. The only time that an atom can give off light is when an electron jumps from one energy level to another. Okay? If it absorbs light, then the electron jumps to a higher energy level. If it gives off light, the electron jumps to a lower energy level. But it can only jump over these discrete energies. So, for instance, if we look at sodium, and we turn sodium into a vapor, low-density vapor, if we put energy into this vapor, heat it up, or pass electricity through it, the gas will glow, but it will glow with a very specific signature. We'll see a weak red line, very strong yellow lines, weak green lines, and weak blue lines. Now, at night, you may have noticed these orange streetlights. Those are sodium lights. And the reason why they have that very distinct orange color to them is because of the spectral lines. The combination of the yellow-orange lines and the other spectral lines give you this sort of orangish, almost pinkish type light. They're very efficient. They produce a lot of light for the amount of energy that you put in them, and that's why they're used. Now, if you were to take cold sodium gas and you were to put bright white light behind it and then put that into a spectrograph, you would see something very different. Instead of bright lines, the white light, which is all colors, would be missing energies at those specific wavelengths. So the sodium atoms, which would give off light at those discrete frequencies, now absorb at those discrete frequencies. So this is a very important process, or a very important phenomena that we use in astronomy to find out what atoms are present. We can look at very hot gases and look at the wavelengths of light that they give off, or we can look at cold gases which are being illuminated from behind and see what frequencies they're absorbing to again identify the atoms that are present. One of the most important atoms in astronomy is hydrogen, and that's primarily because hydrogen is so abundant. It makes up about 75% of all the material in the universe, the normal material. I mean, we get a lot of dark matter, dark energy, and stuff that I don't want to get into right now. But normal matter, about 75% of it's hydrogen. So hydrogen spectra are going to be very important in trying to identify what's going on in a particular object. Now, hydrogen is a very simple atom. It has one electron. So really what that one electron does will determine what we see. There are a very large number of energies that this electron can have, but only a few transitions lead to visible light. And these transitions are very important. These primarily come from the ground state of hydrogen is down here. As we heat hydrogen up and give it more energy, the electron jumps to higher and higher energy states. Any transition with the second energy state and higher energy states produces what is called a Balmer spectrum. So, a lot of the light, a lot of the spectra that hydrogen actually produces is not visible to the eye. Some of it's in the ultraviolet, some of it's in the visible. But if we look at the visible spectra, the hydrogen alpha line, and it's called hydrogen alpha, alpha being the first letter of the Greek alphabet, the hydrogen alpha line, the first line that we can see in the visible, is red. The next line that we can see is sort of a greenish blue. We call that hydrogen beta. Beta is the second letter in the alphabet. Then we have hydrogen gamma and hydrogen delta. Again, gamma and delta are the third and fourth letters in the alphabet, respectively. So, when astronomers were first investigating different spectra, because visible light was the only light that would make it through the atmosphere, these four lines were the most important to investigate, and the hydrogen alpha line was oftentimes the strongest. So again, looking at the hydrogen emission spectrum, if we take a tube of hydrogen and we excite it by putting electricity through it, like in this tube right here, we know it sort of has this almost pinkish, or more properly, magenta glow to it. That is a combination, again, of the red light, the blue-green light, and the violet light. And that produces that very distinct color. Now, that's hydrogen excited. If it's absorbed, okay, it's absorbing energy, such as in a dark line spectrum, you need something brighter behind the hydrogen to produce the visible light. And here we have the absorption lines of hydrogen. And we actually see these in the sun. And although the surface of the sun is very hot, the layers beneath the sun are even hotter and give off more light, and that's where we can actually see these dark lines. Other elements, well, as I said, each element has a different energy level or set of energy levels. Therefore, it's almost like people have different fingerprints, and we can identify people according to the fingerprints that they leave. The atomic spectra are very much like these fingerprints, okay? We can look at the light from these distant objects, see what spectral lines are present, and match their spectral fingerprints to known atoms. You know, in fact, this is the way helium was discovered. Helium, named after Helios, the god of the sun, was actually discovered by looking at the solar spectrum. So, again, looking at this, we can see hydrogen has its own set of lines. Helium's a little bit different. More lines are present. Mercury, fluorescent bulbs, and some of the bluer tinted streetlights contain mercury in them. And the reason why they have this sort of bluish tint is because of these violet lines down here. Other elements, again, you can see mercury, lithium, cadmium, strontium, calcium, sodium, we've already talked about. All of these have very distinct spectral lines, which gives them their unique fingerprints. Here's some more common elements. Now, once again, looking at the sun has what we call an absorption spectrum. Here's a very complete solar spectrum where the light has been put through a diffraction grating and separated into its different colors, from red to orange to yellow to green to blue, and finally to violet. And in the spectrum, we see, so many different elements that are on the periodic table of elements. Some of the lines are darker, some of the lines are lighter, and the darker lines are obviously the elements that are a little more common, and the lighter lines are trace elements. But it tells us a lot about what is in the sun's composition. Again, scientists are able to match some of the magnesium spectrum to the solar spectrum. Here you have a intense blue line right there. Then we can see the corresponding absorption line in the solar spectrum. Here you have hydrogen. Here's the hydrogen alpha line. And you can see that hydrogen alpha line down here. Here's the sodium D line. Here's a sodium D line here. Here's a strong calcium line. There are strong calcium lines down here. Here's a calcium line here. And then, of course, there's some lines found in the iron spectrum, such as this one right here, which we see right there. So, again, it takes a little bit of detective work, but if you analyze the light of the light coming from distant objects, you can actually find out something about the composition, what elements are present. And that's a very important piece of information. Again, most of the universe is hydrogen and helium, but the presence of heavier elements tells us a lot about the processes that are at work, especially when we're looking at older stars, because older stars generate some of these heavier elements that are present. So far, what can we talk about? We can tell the temperature of objects through black-body spectra. We can tell the composition through atomic spectra. Here's something interesting. The sun is entering a phase where activity in the magnetic field is becoming greater and greater, and that can lead to solar storms that affect us here on Earth. And one of the nice byproducts of these storms is that the aurora makes its way further and further south, at least at our location. By looking at the different colors of the aurora, and some of these aurora can be very beautiful, we can tell which elements in the upper atmosphere, way up at the top of the atmosphere, are affected by this this light. And here you can see oxygen produces green and red lines. Nitrogen produces some of the blue that we see, and also some of the red is also coming from the nitrogen. And of course, our atmosphere is primarily nitrogen and oxygen. We even see atomic spectrum all the way in the X-ray part of the spectrum. Now, this is important because although objects don't naturally emit X-rays, it is possible to take samples from other places and irradiate them so they do glow. In fact, that's what some of the Mars rovers do. They have a source of gamma rays or a source of hard X-rays. They shine this on their samples. Samples will fluoresce and tell them exactly what elements are present in rock samples. Here you can see this sample has iron, nickel, and zinc, and this one has a very large number of different elements, but the important ones here are bromine and let's scatter, sorry. Sulfur. Sulfur is what I'm looking for. Bromine and sulfur, which are usually associated with types of rocks which are precipitated out from water. Molecular spectra, again, in space, most things are of low enough density that things are mainly atomic, but you also have molecules that consist of multiple atoms in different regions, but also on the different planets. For instance, we can look at the light given off by a comet, and the interesting thing about the light from a comet is it contains a lot of unusual substances. Cyanide is one of them, and when cyanide was discovered in the comet in the 1800s, everybody thought a comet passing near the Earth would put cyanide in our atmosphere and kill everybody off. Now we know that's not likely to happen. But we also see different species of carbon that we don't see on Earth. So again, here we are looking at the spectra of light to talk about composition. And even minerals have particular spectra. Most of the spectra used to identify mineral composition is actually in the infrared. Here is a spectra of the mineral hematite. Hematite is iron oxide. It's similar in composition to rust, but hematite is a very specific mineral that generally only forms in the presence of water. So, the big question is, did Mars once have water? Could it have supported life? The presence of hematite seems to indicate that at least water was in liquid form. Olivine is a volcanic mineral. Olivine usually breaks down in the presence of water. So its presence tells us just the opposite, that probably water has not been in that location for very long, because olivine would have converted to other elements, if water had been very recent. Carbonate minerals, again, they have their own infrared spectrum. Important again on Mars, because carbonate minerals tend to form only in the presence of water. And there's a lot of the work that these rovers are doing. They're going around, they're looking at the compositions of these different minerals and identifying, what minerals are present, and trying to match the presence of certain minerals to different formations to the presence or absence of water. So it'll tell us a lot about the history of water on the planet Mars. So we talked about infrared spectra, we talked about molecular spectra. We can even look at nuclear spectra. Even the nucleus of the atom has its own spectrum. And something called Mossbauer spectrum is being used by the rovers to identify, again, different minerals. And this shows a spectra in the gamma ray part of the electromagnetic continuum. And this helped identify, again, the presence of different minerals. So, temperature, composition, two pieces of information that are very important. The third major piece of information that we can get comes from something called a Doppler shift. Now, in the Doppler effect, if an object is traveling toward us, the frequencies tend to go higher, the wavelength tends to get shorter. If the object's moving away from us, the waves tend to spread out and get longer. So, if we look at the atomic spectra and we identify the presence of certain elements, we can then look at the position of these spectral lines to get another piece of information. Is the object moving toward us? Is the object moving away from us? And at what speed? One of the important uses of the Doppler effect is in the spectra of galaxies. Now, most stars, like our sun, have very strong calcium lines. They usually sit in the violet or near violet, bluish violet part of the spectrum. However, Edwin Hubble saw that these spectral lines were shifted a little bit for nearby galaxies and a lot for galaxies that were far away. In the most extreme galaxies that we see today, these lines can be shifted all the way to the red. What does this tell us? Well, the greater the shift, the faster these objects are moving away from us. So we can see something about the speed of what's happening. So again, in summary, black-body spectra tells us a lot about the temperature of objects. Emission spectra and absorption spectra can be used to determine the composition of substances. And really, these emission and absorption spectra can be taken in just about any part of the spectra. The infrared part of the spectra tells us a lot about minerals. The visible part of the spectra tells us a lot about what atoms are present in atomic gases. Ultraviolet spectra, generally for emission and absorption spectra, well, that's also present in a lot of different atoms. X-ray spectra, again, is used to identify the atoms that are present in rock samples. So this is something that we use on Mars quite a bit. And then finally, gamma ray spectra can also be used to help identify different atoms in minerals and different types of minerals. Finally, the Doppler shift gives us a speed. So temperature, composition, and speed go a long way to explaining what we're observing. Okay. Well, that's it for today's presentation. I will put together our next presentation on Chapter 4.